All right, welcome to the first video in this series on real analysis. Real analysis is usually what people think of as the first real math class, no pun intended. Well, it's kind of intended. But it's a very rigorous and proof-heavy math class. It's different than calculus where you're just calculating a bunch of things and solving equations, finding x, blah, blah, blah. You're actually proving things, you're actually finding things, you're actually explaining things. But what is real analysis? We have this concept of real numbers here. The real numbers, you might see this little R notation that's referring to the real numbers. You can't really define real numbers so easily. It may seem like a contradiction, but the whole point of a real analysis, well, part of the point of a real analysis class is to actually define what the real numbers are and see how they're defined very rigorously. But most mathematicians or most math students have an understanding of what real numbers are. They're numbers that they can be, well, they're all numbers, including, whole numbers, rationals, and irrationals, basically, is the informal way to explain them. They don't include the complex numbers, but they're numbers that can be of any form, like 3, 5, 7 repeating. It can be pi, it can be e. Those are the real numbers. But what's real analysis? Well, we'll have to take a step back in the history to really understand what analysis is and why it's related to calculus. And about, well, I don't know. I don't know my history exactly, but around 400 or 500 years ago, some guy named Isaac Newton came along, and the apple fell on his head. There's this apple tree, and this is the best I can draw of a tree. Here's a Newton. Apple falls on his head, and he says, "Oh, gravity, gravity, physics, physics." So Newton and his buddy, not really his buddy, Newton and some other guy named Leibniz. Here's Newton. Here's Leibniz. They both invent basically what we would consider to be called calculus in today's vocabulary. It was used for physics. It was very foundational for physics. Newton and Leibniz didn't really just invent calculus. They kind of invented, the whole mathematics behind physics and mechanics and everything of that sort. However, a lot of more formal and more, you would call them pure mathematicians, hated this concept. They thought Newton and Leibniz were kind of using magic here. They're like, well, you got all these equations, you have all this physics, but it doesn't seem to be very rigorous. We need to define it better. They were using the concept of limits. I'm sure you all know what limits are. But Newton and Leibniz were just kind of calling limits small. They were just like, oh, think of limits as, what happens when intervals get very, very small. And that's kind of how we intuitively think of them. That's what a limit is. That's how they teach you in a calculus. It's not a very rigorous definition. So maybe 100, 200, 300 years later, once again, I don't know my history well enough, but Euler and a few other mathematicians took a stab at, formalizing calculus very rigorously. But eventually along came this guy from France called Cauchy. And Cauchy was a genius. He was a guy who got this whole boat started. He got this whole process kicked off. He actually introduced the whole delta epsilon notation, defining limits and sequences, limits of functions, and all that. And Cauchy was the one that started to actually formalize all the math that Newton, Leibniz, and their successors had created. He started to formalize limits, the concept of continuity, convergence, all that sort of stuff. And he made it more rigorous. So once again, this guy's name is Cauchy, Augustin Louis Cauchy. Very smart guy. He also basically invented, quote unquote, I don't know if that's the right term, but he basically came up with analysis, and he basically came up with both real and complex analysis. And then a guy named Karl Weierstrass, I assumed he's German, but I don't really know. I didn't look it up. He also helped formalize it on top of Cauchy, so he kind of brought Cauchy's findings to perfection, you could say. And then there were other guys like Riemann and Cantor, and they helped formalize all this analysis. So that's what analysis is. It's basically it came to birth. Real analysis came to birth from concepts in calculus, complex analysis. Not what this course is. Not what this series of videos is about. Maybe I'll make a separate one for that. But this is what real analysis is. It's going to be analyzing real functions, real numbers, basically proving theorems you learn in calculus. That's what real analysis is in a nutshell. So in the next video, we're going to dive right in. We're going to do deep dive into, not really a deep dive, but a basic dive into sets and functions. This is a little informal table of contents here. So we'll start off with sets and functions. I guess there we'll go on to sequences, limits of sequences, then we'll do series, then we'll do continuity. And after continuity, I think we go to derivatives, differentiation, and then we go to integrals. And then, yeah, that's basically everything you would learn in the normal analysis class. Probably something else I'm forgetting, but we'll get to it later on.